Hello again. The Basis of Modern Science. Oh yeah, Chapter 2. The Newtonian Concepts, Space, Time, Mass. The ideal aim of science is to give a complete mathematical description of phenomena in terms of the fewest principles and entities. We have to find, under the baffling variety of nature, the essential and irreducible elements whose combinations produce that variety. The attempts can claim to be successful so far only for those sciences that ignore the chemical, living, and mental properties of bodies. The primary concepts in terms of which the science of physics is constructed, such concepts as force, energy, mass, velocity, acceleration, momentum, etc., torsion, have to be supplemented by others in the science of chemistry and, for the sciences of life and mind, are so far from being sufficient that they have hardly yet been found to be even relevant. The mathematical description of nature, therefore, is possible so far only for a limited region of phenomena. Whether such a description is even theoretically possible for the whole of nature is not a question that can be decided on this evidence. The doctrine of materialism is a doctrine that such a description is theoretically possible and, further, that the description would proceed in terms of the concepts mass, energy, acceleration, etc., that have been used in physics until recent times. This doctrine has no longer any plausibility, since the concepts in question have been found inadequate even in physics itself. But the inadequacy of the old concepts does not, of course, affect the theoretical possibility that a mathematical description of the whole of nature may be given in terms of the new concepts, or, if not in those, in terms of concepts not yet invented. The question is of no importance except that it enables us to realize the nature of our general assumption. Either we suppose that phenomena possess aspects that cannot be described mathematically, and that therefore science is a partial description of nature, since it deals only with those aspects that are mathematical, or we suppose that the present partial description given by science is due merely to the fact that its present technique enables it to deal only with the simplest cases. That is, we may suppose that those phenomena which do lend themselves to scientific description are described exhaustively. When, for instance, Newton says, "It seems probable to me that God in the beginning formed matter in solid, massy, hard, and penetrable, movable particles, of such sizes and figures, and with such other properties, in such proportion to space, as most conduced to the end for which he formed them, and that these primitive particles, being solids, are incomparably harder than any porous bodies compounded of them, even so very hard as never to wear or break in pieces, no ordinary power being able to divide what God himself made one in the first creation." Are we to suppose this list of properties of the ultimate particles to be exhaustive? That Newton himself thought so is very doubtful. Most of his followers, however, did think so. It was this belief that nothing existed but the primitive particles, and that these particles were exhaustively described by their mathematically definable properties, that enabled Laplace to say that a sufficiently great mathematical intelligence, given the distribution of the ultimate particles in the primitive nebula, could deduce the whole future history of the world. This extraordinary act of faith was prompted by the fact that the Newtonian set of abstractions, space, time, mass, enabled a complete description of the phenomena of motion to be given. For a long time, these three concepts, as Newton formulated them, were the cardinal concepts of the science of physics. Other concepts used in physics were derivative from them. Thus, a velocity is the rate of increase of distance with time. Acceleration is the rate of increase of velocity with time. Momentum is the product of mass and velocity, and so on. In an account of modern scientific ideas, therefore, we must begin with these three cardinal conceptions. The notion of mass is necessary, as we have said, to make possible the mathematical description of the motions of material bodies. Two bodies may be of the same geometrical size and shape, and yet, under the influence of a given impact, acquire different motions. This is, of course, one of the commonest facts of experience. Golfers do not play golf with little cannonballs, but to disentangle the particular property of matter that is responsible for this difference was not easy. The property is constant for the same piece of matter. A given impact will always produce the same amount of motion in the same body. The property in question is not the same thing as the weight of the body. A body at the equator weighs less than it does at the North Pole, and on a journey to the moon, it would reach a point where it weighed nothing. Nevertheless, it would always acquire the same amount of motion through the same impact. The weight of a body depends on its position relative to the center of the earth. The property we are trying to disentangle is independent of the body's position relative to surrounding bodies. This property Newton called mass. In defining mass, he assumed the notion of force, and this notion has since become highly sophisticated or even dissolved away altogether. But the Newtonian notion of force was based psychologically on the common human experience of muscular effort. The ordinary human experience of pushing and pulling was the basis of the scientific conception of force. Bodies which attracted one another were vaguely supposed to be pulling at one another, and this pull was usually supposed to be transmitted through some intervening medium, an ether. Now, Newton stated that the effect produced by a given force, whether that force was a push or a pull, depended not only on the force, but on the mass of the body on which it acted. And he gave a precise rule by which the force could be measured, whether the body was at rest or in motion. For the action of force is measured by the change of motion of the body. If the body is originally at rest, this change of motion is, of course, the whole motion. If the body is already in motion, the action of the force is to change the motion. But the change of motion for a given force depends on the mass of the body. The more mass of the body, the smaller the change in its motion for a given force. Newton stated that the force was precisely measured by taking the product of the mass and the change of motion. In speaking of change of motion, we mean the change that occurs in a definite standard interval of time, say 1 second. Change of motion, so defined, is called acceleration. Newton states, therefore, that the force acting on a body is equal to the body's mass multiplied by its acceleration. This celebrated law has an aspect that deserves attention. It defines mass in terms of force and force in terms of mass. The one directly observable quantity introduced is acceleration. If we start by knowing force, we can obtain mass in this way. If we start by knowing mass, we can obtain force. But the definition merely defines them in terms of one another. It would seem that either mass or force is a superfluous concept. We can, however, obtain the mass of a body experimentally without introducing the notion of force at all. If we allow different bodies to collide, their velocities after collision are usually different from their velocities before collision. If we allow different bodies to collide, their velocities after collision are usually different from their velocities before collision. But there is a certain simple function of the velocities before collision which has the same value as that same function of the velocities after collision. This function involves coefficients, one for each body. These coefficients are the masses of the bodies concerned. The layman may feel that this procedure is merely a device and not a discovery. The difference in science is not clear, but the merit of this device, if it can be so called, lies in its usefulness. For when, by our collision experiment, we have determined the mass of a body, we find that this mass is quite independent of that particular experiment. We get the same value for the mass of that body, whether other bodies we make it collide with. We get the same value for the mass of that body, whatever other bodies we make it collide with. Hence, we have discovered a characteristic of this body which, within the conditions of these experiments, remains invariant. Further, this characteristic remains invariant in all conditions of temperature and is quite unaffected by the presence of surrounding bodies. It has thus a high degree of permanence and is therefore important. We suppose also that it persists unaltered through all chemical changes. The mass we obtain from the collision experiments is called the inertial mass of the body. It is the mass, we may say, that is concerned in impacts between bodies. But a body also possesses another characteristic called its gravitational mass. All bodies, as we know from the most famous of all scientific laws, Newton's law of gravitation, attract one another. The degree of this attraction depends upon their distances and their masses, we are told. But the mass mentioned here is not obviously the mass involved in the collision experiments. The mass involved in those experiments owes nothing, so far as we can see, to that mysterious power of attraction that all bodies exhibit. It would exist, we may suppose, even if bodies did not attract one another at all. The mass involved in gravitation appears to be like the charge on electrified bodies, an entirely separate thing. We measure its amount by making attraction experiments, as we before made collision experiments. We find that it also remains invariant. And we make the astonishing discovery that the relation between a body's inertial and gravitational mass is exactly the same as for any other body. This relation is entirely independent of the physical conditions or chemical constitution of the bodies concerned. No other two properties of a body are linked together in this indissoluble way. If we could, in some way, alter the inertial mass of a body, we should apparently be justified in supposing that we would thereby alter its gravitational mass to just the same extent. So strictly and invariably connected are they. This fact suggests the apparently wild idea that in talking of the inertial and gravitational masses of a body, we are really talking of the same thing. As if we spoke of a body's size and also of its magnitude, we say apparently wild idea, because if it were true, we should have to say that a body's gravitation was merely a manifestation of its inertia. Torsion. The idea is so wild that it seems to have occurred to only one man in the history of science. As a result, we have the tremendous scientific revolution called Einstein's general principle of relativity. At the present stage of our discussion, however, we shall ignore this development and assume that we have satisfactorily isolated a fundamental property of matter called mass. Referring by this term indifferently, either to inertial or gravitational mass, as we are justified in doing because of their absolutely strict proportionality. Having isolated the notion of mass, Newton proceeded to give a complete account of the motions of material bodies conceived as masses moving in space and time. We must now therefore pay some attention to his conceptions of space and time. It is best to give these conceptions in his own words. Absolute, true, and mathematical time, of itself and from its own nature, flows equably without regard to anything external, and by another name is called duration. Relative, apparent, and common time is some sensible and external, whether accurate or unequable, measure of duration by the means of motion, which is commonly used instead of true time, such as an hour, a day, a month, a year. Absolute space, in its own nature, without regard to anything external, remains always similar and immovable. Relative space is some movable dimension or measure of the absolute spaces which our senses determine by its position to bodies, and which is vulgarly vulgarly taken for immovable space. Sorry. Such is the dimension of a subterraneous, an aerial, or celestial space determined by its position in respect of the earth. Absolute and relative space are the same in figure and magnitude, but they do not remain always numerically the same. For if the earth, for instance, moves a space of our air, which relatively and in respect of the earth always remains the same, will at one time be one part of the absolute space into which the air passes. At another time it will be another part of the same, and so, absolutely understood, it will be perpetually mutable. That's it for now. Thank you.